Hello and welcome. This is chapter number 8 and we are talking about second order circuits. So in this lecture, we'll be talking about solving general second order circuits. So the thing is how we are going to solve a general second order circuit. So in our textbook or in the Sadiku's textbook, which we are following, it gives us 4 steps in which we can solve any general second order circuit. The thing we have to remember here is that the previous circuits which we have solved till now, they have resistor, capacitor, and an inductor. So it is a or either these components are connected in series or either these components are connected in parallel. So in general, in second order circuit, there may be there may be two inductors, there may be two capacitors, there may be inductor, capacitor, resistor, and not necessarily connected in series or parallel combination. There can be any combination, but the thing is we have two storage elements, either two inductors, either two capacitors, or inductor and a capacitor. So how we are going to solve those circuits which are not exactly in series or which are not classified exactly as parallel circuits. So in order to solve these circuits, there are 4 different points which are given in the textbook. So first of all, it says that determine the initial conditions, that is x of 0 on dx 0 by dt, and the final value x of infinity, as we have seen earlier. So this will be our first step. The second step will be we have to turn off the independent source and find the form of the transient response by applying KCL and KVL. Once the second order differential equation is obtained, determine its characteristic roots. Depending on whether the response is overdamped, critically damped, or underdamped, obtain the transient response with two unknown constants. Third step, obtain the steady state response, x steady state of t, which is equivalent to x of infinity, and which is the final value of x of t as we have calculated in the first step. The overall response or the total response is now found or is now found as a sum of transient response and steady state response, that is x of t equals to sum of x of transient plus x of steady state. From here we determine the constants associated with the transient response by imposing the initial conditions and determine initial conditions as we have calculated in step number 1. So let's solve a few examples and see how we solve a generic second order circuit. So in our textbook, this is example number 8.9 of from our textbook. It says find the complete response V and then I for time t greater than 0 in the circuit as shown in figure 8.25. So this is the circuit that is shown. So here we can see that we have an inductor and we have a capacitor. So we have two storage elements. It means that our overall differential equation will be of second order. Secondly, we can see that there is no characteristic parallel or series combination of the inductor and the capacitor. So this is a generic circuit. So how we are going to solve it? So our first step, remember from the previous slide, determine the initial conditions and the final condition. So number 1, determine the initial conditions. So we have to determine the initial conditions. So let's see how the circuit looks as. For the initial conditions, we first of all check before t equals to 0 or before switching, how the circuit looks like. The circuit before switching will look something like this. So before switching, the circuit will look something like this. Current I, this is 1 Henry. This is, so the current looks something, the overall circuit looks something like this before switching. And this circuit is in this state for infinite time. So, I mean, we don't know. So what is happened here? The capacitor is completely charged and the inductor is completely magnetized. So the equivalent circuit in this state will look something like this. This is 12 volts. This is my 4 ohm resistor. My inductor will be behaving as a short circuit because it is completely charged, and my capacitor will be behaving as a open circuit. Okay. So now what is the VC 0 negative and IL 0 negative? What is the value of current and voltage here? So we can easily see that we have IL 0 negative is equal to 0 amperes because this is an open circuit, no current is flowing. Similarly, VC 0 negative is equal to 12 volts. Since it is open circuit, all the source voltage will be appearing across these terminals. So from here, what we can see that, or what we know from an inductor is VL is L di by dt. It means that the current does not change instantaneously in a inductor. Similarly, C dV by dt. This means that the voltage across the capacitor does not change instantaneously. So we know that. So therefore, we can say that IL 0 negative is equal to IL 0 positive is equal to 0 amperes. So this is our first initial condition. Our second initial condition will be VC 0 negative equals to VC 0 positive equals to 12 volts. So this will be our first initial conditions. Okay. Then we have to find out the other initial conditions, that is dV by dt 0 positive. This is what we have to find out. So now, or we have to find out di by dt 0 positive, any of these. So let's say we find out dV by dt first. So that will also help us in solving this question. So for finding out dV by dt at 0 positive, it means that our circuit has been switched. So just after switching, the circuit will look something like this. So equivalent circuit will look something like this. Okay. So this is plus minus V naught. This is my 1 Henry inductor. This is 4 ohms. This is 2 ohms. And my switch is closed. This is 12 volt battery. So now the switch has been closed. So what will be the value of dV by dt, or if we have to find di by dt? So this is basically the current that is flowing, and this is the voltage V which we are concerned with, not V naught. It is just simply V. Okay. So let's try to solve this question. So this is, say, my node A. So I will use the next slide for it. Before going to next slide, let's try to solve. So at node A, what we are seeing, so we are seeing that a current I is coming from here. A current IR is going this direction, and a current IC will be going to this direction, or the capacitor current will be. So I will be equal to IR plus IC. So we can write the equation or the node or the current entering or leaving at the node A using the Kirchhoff laws in this fashion. Okay. So at time t equals to 0, we can write that I of 0 positive is equal to IR 0 positive plus IC 0 positive. Okay, so we can easily write this equation for node A. So so at, and I'm redrawing it, at node A, we got IR 0 positive equals to plus IC 0 positive equals to I 0 positive. So this is, for example, this is our node A. this is how this equation will look like. Okay, and we know that IC, or the capacitor current, is given as C times dV sorry, C times dV by dt, right? So we know that. So this thing, if I at we are talking about zero positive, we can easily find out C times dV zero positive by dt, right? So just replace IC by C dV by dt. So IR, so again, so what will be the value of IR? So the circuit will look something like this. Let me draw it again for convenience. This is voltage. This is our capacitor of 0.5 farad. This is 2 ohms. This is 4. This is 1 Henry. And we are talking about here. So this is I. This is I R. This is I C. So we know that the capacitor voltage does not change instantaneously. So at time t equals to 0, the voltage that is appearing across, or we can solve it, VR 0 positive, will be equal to 12 volts, or that is equal to VC 0 positive, right? So we can easily write IR at 0 positive is equal to VR at 0 positive divided by the resistance, and that is 12 divided by 2 ohms, that is equal to 6 amperes. So we can say that IR is equal to this. Similarly, we know that I 0 positive is equal to 0 amperes, and so now we have these two values with us, and we know that IC 0 positive is equal to this. So let's put it in the values. We get I so 6 plus C times dV 0 positive by dt is equal to 0. This becomes dV 0 positive divided by dt minus 6 divided by 1.2, that is the capacitance. This becomes minus 12 volts per second. So this becomes my second initial condition, or sorry, the third initial condition. So now we have I 0 positive is 0, V 0 positive as 12, and dV 0 positive by dt as minus 12 volts per second. So we have these two initial conditions with us. So it's better to develop the voltage equation first, and then using that voltage equation to solve our answer or solve our question. Okay. Now, also, then the next step is find steady state values. So for steady state value, it means that at time t equals to infinity. So at time t equals to infinity, our circuit will look something like this. So our circuit will look something like this, and the equivalent circuit will be, the inductor will be completely magnetized or will behave as short circuit. With 2 ohm resistance, this will be an open circuit. This is 12, this is 4, 1 Henry, 2 ohms and 0.5 farads, right? So this is open circuit. So again, V at infinity and I at infinity. These are the two values which we have to calculate. So I at infinity. So I at infinity, just the current that is flowing through the circuit. So the current will be 12 volts divided by 4 plus 2, 6, and means that 2 amperes. Similarly, V infinity will be the voltage across 2 ohm resistor. So the voltage will be 2 ohms divided by 4 plus 2, 6, multiplied by 12. That is equal to 4 volts. Okay. So my steady state conditions can be easily calculated like this. Okay. So now we have both our initial conditions and our steady state conditions. Then the second step, solve for transient response. Okay, solve for the transient response. Okay, so for solving for the transient response, what we have to do, remember this slide. Turn off the independent sources and find out the form for the transient response by applying KCL and KVL. So let's just simply turn off the source. So turn off the source. Our circuit will look something like this. So this is our equivalent circuit. This is inductor. This is 4 ohm. This is 1 Henry. This is 1.2 Farad. This is my voltage. This is the current we are concerned with, and this is 2 ohms. So this is ground source. So, okay, so now this is our effective circuit. So we have to basically find out the transient response, and in order to get the transient response, we basically need to know the differential equation for the circuit. So let's try applying KCL and KVL for this case. Since we have both inductors and capacitors, we have to use both KCL and KVL for solving this circuit. Remember the case that if we have only inductors with us, say it is something you may always remember or may try, it works generally. So if we have inductors with us, generally applying KVL gives you better results, and for capacitors, generally applying KCL will be more suitable or will give us better results or will be much easier to solve. Okay, so first of all, for in the circuit, we develop this, we at node A applying KCL. So we have done this already. So applying KCL, what we get? So we get I that is coming in, I that is going out is equal to IR plus IC. I as it is, IR is IR. So basically this node voltage V appears across this R. So we can write V divided by R plus IC is C times dV by dt. So this is my equation for, or when I apply KCL at node A, this is what I get. So simplifying it, so V divided by resistance 2, capacitance 1 by 2, dV by dt. So this is my first equation for this circuit, right? So now, so we have applied KCL. Now what we have to do? So this is, we can see again, drawing the circuit for convenience. So what we see here, or say 1 Henry, 4 ohm, this is 2 ohms, and this is 0.5 Farad plus minus V. So this is again, say this is our loop 1, L1. You can call it loop 1. So let's for loop 1, or you can call it L1, applying, remember loops are KVL. Applying KVL, we get what? So this is the current I that is flowing. So 4I plus voltage across this is called VL plus this node voltage. So again, we are not much concerned with whatever this loop current is. We are more concerned with this node voltage, and this node voltage is V naught. So we can always write this as V. This is the node voltage V. This is appearing here. This is basically the voltage that is appearing across this voltage. So we can write this equation as this. So what we get 4I plus VL is in L times di by dt plus I keep it as in terms of V becomes this. So putting in the values and simplifying, so we get inductance is 1, so 4I plus di by dt plus V equals to 0. So this is basically our equation number 2. So now we have two equations, two differential equations, one in terms of both having current and voltage as undefined variables. So the question lies here that in which form we have to convert it. Either we have to convert it into a voltage only differential equation, or either we have to convert it into a current only differential equation. So this decision is made based on what are the values of initial conditions you are easily able to find. So you are easily able to find the values of I naught, V naught, and dV by d naught. So this is more important. So voltage, for voltage you have both the initial conditions which are required to generate or to solve these equations for the final coefficients a1 and a2 or b1 or b2, whatever you want to call them. So we convert it into a voltage, or these equations into a voltage only differential equation. So using these equation 1 and 2, we, so remember, using equation 1 and equation 2, we convert it into a voltage only second order differential equation. And reason being, because we have V0 positive and dV0 positive calculated with us. Okay, so we have both V0 positive and dV0 positive calculated with us, so it will be easier for us to solve solve this differential equation. If we have I0 positive and di by dt0 positive with us, we would have convert this equation, these two equations, into a current only differential equation. So solving EQ1 and equation 2, or we can call it put equation 1 in equation number 2. So wherever we have I, put values of I into equation 2, we get 4 into I is V by 2 plus 1 by 2 dV by dt plus di, okay, so d by dt of V by 2 plus half dV by dt plus V equals to 0. So if we are going to simplify this equation, what we get is dV square by dt square plus 5 times dV by dt plus 6V equals to 0. So if we are going to simplify this equation, this thing becomes something like this. So this can be written as s square plus 5s plus 6 equal to 0. And we have seen this, how we write this thing in our previous lectures. And then we find out roots for the characteristic equation. So remember, this is the characteristic equation. So this is the characteristic equation. So roots are S1, second order equation. We have two roots. S1, we call it -2. S2 is -3. So we have real and distinct roots. So the response will be overdamped. So response will be overdamped. So we can easily write V of t transient response a1 e raised to power minus 2t plus a2 e raised to power minus 3t. So this is the way we write the transient response for such a case. So remember the overall response. So overall response, this is our step 4. So overall response is V of t transient response plus steady state response. So what is the value of V steady state? So V steady state of t is basically V steady state at t equals to infinity. Vt equals to infinity. What the voltage or the voltage initial condition was 4 volts, right? So this is V steady state of t is 4 volts. We have this value, so our voltage function will look 4 plus a1 e raised to power minus 2t plus a2 e raised to power minus 3t. So this is how our voltage function will look like. Number 5, solve for a1 and a2 using initial conditions we have. So our first case, V0 positive is equal to 6 volts. So V0 positive is equal to 6 volts. We use this initial condition. Sorry, V0 positive was 12 volts, not 6 volts. So 12 volts. We use this initial condition. So we have 12 equals to A1 plus A2 plus 4. So basically, how we develop this thing, I'll write or I'll solve it for you. So V of T0 is equal to 12 equals, that is equal to this equation. So this is the basically overall response. I call it by A. Put in A. 12, 4 plus A1 e raised to power minus 2, time value is 0 plus A2 e raised to power minus 3 into 0. So this becomes 8 equals to A1 plus A2, and I call this as my equation number 3. Okay, then I use dv 0 positive by dt, that was equal to minus 12 volt per second, if I'm not mistaken. Let's go and check. Yes, minus 12 volts per second. So minus 12 volts per second. So first we differentiate this thing. So dv dt at time t equals to 0. This becomes differential of 4 will be 0 plus minus 2 a1 e raised to power minus 2 into 0 plus minus 3 a2 e raised to power minus 3 into 0. This becomes equal to, or this thing is equal to minus 12 as well. This thing can be written as minus 12 minus 2 a1 minus 3 a2, or 12 equals to 2 a1 plus 3 a2, and I call this as my equation 4. Okay, so now we have two equations, equation 3 and 4. If we solve these equations 3 and 4 simultaneously, so solving equation 3 and equation 4 simultaneously, we get a1 equals to, so I'm just simply writing a1 equals to 12 and a2 equals to minus 4. So my voltage value will be 4 plus 12 e raised to power minus 2t minus 4 e raised to power minus 3t. So this will be the value for the answer for the voltage. So complete response for voltage would look something like this. Now Now question is calculate value of current I or response value of I of t. So remember I equals to, so we go and check our initial equations with which we develop. I can be calculated from these two. So this one was the value of I is V by 2 plus half dV by dt. So just put the value of voltage in this equation and we get I. We remember I is V by plus half dV by dt. So I will be equal to 4 divided by 2, 2 plus 6 e raised to power minus 2t minus 2 e raised to power minus 3t plus 1 by 2. Differential of this will be minus 24 e raised to power minus 2t minus plus 12 e raised to power minus 3t. This will be the value. So the value of I of t will be, if we are going to add all these, 2 minus 6 e raised to power minus 2t plus 4 e raised to power minus 3t. So this is the value of I which we have for this circuit. So remember, so the value of I is this. I'll write the value of V again for you. So value of V was 4 plus 12 e raised to power minus 2t minus 4, I think 4 e raised to power minus 3t. So this one was the value, and let's cross check. 12 4 minus 4. So yes, okay. So this is how or we calculate these values. So once we calculate the value of voltage, we use the value of voltage to find out the value of current in the circuit with the equations which we have developed in our earlier process. So this is how we develop our response. So let's try to solve another question. So example 8.10 of the textbook. In this textbook, it asks us to find out the value of V naught. So we have to find out the value of V naught for time t greater than 0. So for time t greater than 0, we have to find the value of V naught in the circuit. So let's see how the circuit looks. So in this circuit, we have a resistor 3 ohms, and then I have an inductor, then another resistor, and then there is an inductor that's connected in parallel with that resistor. So what we see here is that we do not have any capacitor in the circuit. So question is it a second order circuit? Yes. This is a circuit, second order circuit. Why? Because there are two storage elements. So when we have the number of storage elements is equal to the degree or the of the circuit. So third order circuit will have 3 storage elements, fourth order circuit will have 4, and so on and so forth. So similarly, this circuit have two storage elements, the 2 inductors. So remember in our previous slide, I wrote one thing. So for inductor, it's good to use KVL. So remember this point while solving this question. So first case, how we solve it? First point, find initial conditions. Initial conditions. So remember for inductor, it's generally you're good to use KVL. Okay, so it's good to use KVL, but we'll see. Find initial conditions. So find initial conditions. So before t equals to 0, how the circuit looks like. So this is 7 u of t. So it means that the voltage waveform or the voltage function was 0 before time t equals to 0, and after that it is 7 volts. So time t equals to 0, it was 0 volts, and after time it's a unit step function of 7 volts. So before time t equals to 0, the circuit was something like this. This is 0.5 Henry. This is 0.2 Henry. This is 1 ohm plus minus V naught. We have to calculate here. And this is 3 ohm. Okay, so the circuit is like this, and this is in this state for infinite time. So we can assume that the inductors will be completely magnetized, uh, and the overall circuit will be something like this. 3. This is I1. This is I2. This is 1 ohm. 0 negative, I2, 0 negative. So I call it IL1, IL2, inductance 1, inductance 2. So basically we do not have any voltage or current source in this. So we can easily write that IL1 0 negative is equal to 0. IL2 0 negative is equal to 0 ampere. So the initial conditions for current for both of these circuits, for both of these inductors is, or both of the inductors are magnetized to 0 amperes of current before this voltage source comes into play. And from here we can easily say that IL0 negative is equal to IL10 positive is equal to 0. Remember, because L times di by dt is the voltage across the inductor, and it basically shows that the current does not change instantaneously. Instant change not allowed. Similarly, we can write as IL2 0 negative is equal to IL2 0 positive is equal to 0 amperes. So these are our first two initial conditions for our circuit. Okay, so now our second part is so what about so let's find either di 0 positive by dt or dv 0 positive by dt. So we have to find any of this, any one of this. If we are able to find out, we will be good. Okay, so let's try. The thing is, the equivalent circuit will be after time t equals to, or after time, or at time t equals to 0 positive. The switching circuit will look something like this. So this is 0.2 Henry. Again, this is 0.5 Henry. This is plus minus V naught, 1 ohms, and this is 3 ohms. This is 7 volts. Okay, so we have to basically find out uh, the initial condition here. So let's divide this into two loops. So this is say L1. This is my loop 2. L2. So we can just simply, for this is an inductor, so apply KVL. So we can just simply applying KVL or writing loop equation for loop 1. So for loop 1 we get 7 uh, equals to 3 times I1, we call it I1 plus VL plus this voltage V naught 0. All right, so V naught 0. So at t equals to 0 positive, we can write at 3 times I1 0 positive plus VL 0 positive plus V naught 0 positive, right? So we can easily write this thing. So the thing is, VL, we know that is equal to L times di by dt, or VL 0 positive will be equal to inductance times di 0 positive by dt. So we can replace VL by this value. Yes, I 0 positive is 0. So we know that from our IL1 0 positive is equal to 0. So this value becomes 0. What is the value of V naught 0 positive? So remember what, so V naught 0 positive. So V naught 0 positive will be 1 ohm resistor. And what is the overall current that is flowing? Overall current is I1 0 positive minus I2 0 positive from this equation. So if we have this loop I1 and this is the loop I2, so I1 minus I2 at 0 positive. So again, both of these currents are 0. 0 minus 0. So overall this value is 0 volts. So this value is also 0 volts. So let's put in the value or plug in the value 7, 3 into 0 plus inductance. Inductance is 0.5 here. Di 0 positive by dt plus 0, and this di is di1. Remember, so for inductance L1. So uh, for this loop L1, so in this loop we have only one inductor, so we have we are good with that. So this equation will give us the value of di 0 positive by dt, and this value becomes 14 amperes per second. This value is 14 amperes per second at time t equals to 0 positive. So now what we see here is that we have I0 positive for I1, and for I2 we also have 0 positive equals to 0, and this value is, and we have di1 0 positive by dt equals to 14 amperes per second. So these are some of the initial conditions we have. Also add the initial condition V0 positive over here as well. So this is another initial conditions we found out, voltage and current. So these are the initial conditions we have. So we can easily see that we have two initial conditions for current one. So for this current I1, we have both initial conditions. So it's good to develop the differential equation for this current I1. So let's do that. And sorry, before that, find steady state value. So for steady state values, after time infinity, so this circuit will look again plus minus. This is 7 amperes. This is 0.5. Let me redraw it. So this is so remember, after time t equals to infinity, uh, this is the value of I1 that is flowing here. This is 1 ohms. After time equals to infinity, this is a 0.5 Henry. This is 0.2 Henry. So at time infinity, this circuit will look something like this. So that these inductors will be completely magnetized, means that they will be behaving as a short circuit. So this is how the circuit will look like. So this is a short circuit. And so this is my I2. This is my I1. This is 3 ohms. This is 1 ohm. This is a 7 volt. So I1 at infinity will be 7 divided by 3 amperes, and this is same as equal to I2 at infinity, 7 by 3 amperes. So both values is the same. So we have found out the values which will be there at infinity for both of these circuits. Okay. So from here, we also find say what will be the value of voltage. So VL1 at infinity, again this is 0 volts, and this is again similar to VL2 at infinity, that is also equal to 0 volts. Okay. This is how yes, so this is how we can say that these are all the values of the current and voltage at infinity. So remember, so VIL1 is, sorry, this is a wrong way to write it. It's not necessary at the moment. So V naught, the other equation we need. So V naught at infinity. So this is what we need, because this is the voltage variable we are trying to find. So V naught at infinity will be 1 ohm I1 infinity minus I2 at infinity. This is how we calculate it. So both will be equal to 1, 7 by 3 minus 7 by 3. This becomes equal to 0. volts. This is how. So we can say that V naught at infinity is equal to 0. V naught at infinity is equal to 0. So we are good. So these are our uh, initial conditions for the steady state conditions for this case. So now what we can see here, that we have our initial conditions and we have our steady state values for this equation. So now the second part is solving for transient solution. So solving for transient solution, uh, first part we have to do is we have to ignore the current sources, or independent sources. So basically we ignore them and draw the circuit without them. So our circuit would look something like this. So this is how our circuit would look like. This is how our circuit will look like. So this is my loop 1, L1, and this is this is my I2, this is my I1. So now just simply using KVL and getting the loop equations, we get, just simply use the KVL. So we get 3I plus voltage across this inductor plus V naught, and so V naught is I1 minus I2 multiplied by the inductance value, and this is equal to 0. So I can just simply write this as 3I plus this is so 1 by 2 inductance di1 by dt. So VL1 equals to L dL1 di1 by dt. So this is my L1 inductor, this is my L2 inductor. So I call it this as an L1 inductor, this as L2 inductor. Okay, so di by dt plus I1 minus I2. Simplifying it, I get I2 equals to half di1 by dt plus 4 times I1. So this is my first equation that can be written like this. So uh, from loop number 2, we get L2 di2 by dt plus I2 minus I1 into 1 equals to 0. So overall, we get 1 by 5 di2 by dt plus I2 equals to I1. So this is my equation number 2. So from equation 1 and 2, we get solving from solving equation 1 and 2, we get basically or in an easy way, uh, we have initial conditions for I1. So better to get the remember, uh, better to have second order differential equation in terms of I1, right? 1. So let's find out. So the overall differential equation, second order, if we get, it will be di2 by dt square, this is di1 plus 13 times di1 by dt plus 10, plus 30i 1 equals to 0, and we can easily reduce it in characteristic equation in terms of s. This is s square plus 13s plus 30 equals to 0, and from this we find out the roots. So the roots are s1 and s2. The roots are 10 minus 10 and minus 3. So s1 is minus 3, this is minus 10. Again, these roots are real and distinct, so the response will be overdamped, and the overdamped response will look and this is I1, so I1 of t will look a1 e raised to power minus 3t plus a2 e raised to power minus 10t, look something like this. So I1 will look something like this. So then we have to find out the overall response. So overall response, remember I1 of t is equal to I1 transient response. So this is the I1 transient response plus I1 steady state response. So the steady state response, remember we are talking about I1. So the I1 steady state response was 7 by 3 amperes plus A1 e raised to power minus 3t plus A2 e raised to power minus 10t. So this is my complete response or the overall response. Now we have to find out the values of A1 and A2. So finding values for A1 and A2. Okay. So finding values for A1 and A2. How we find out these values? First of all, we have I of t, again writing for simplicity, plus A1, so I1 of t. A1 e raised to power minus 3t plus A2 e raised to power minus 10t. So remember, first initial condition, I1 0 positive is equal to 0. So put I 0 positive equals to 0 here. We get 7 by 3 plus A1 plus A2. So this becomes my first initial condition. Oh, sorry, my first equation. This is so we can say it as A1 plus A2 equals to minus 7 by 3. This is my first equation. My second equation, use d I1 0 positive by dt. What was this value? Remember, this value was 14 amperes per second here. So remember, this is where we calculate that. So using this value, we get this value is 14. So 14, we just multiply it over here. So we get minus 3a1 minus 10 times a2. So my second equation will become 3a1 plus 10 a2 equals to minus 14. So this is my second equation. It's equation 1. This is equation number 2. So solving sorry, I'll call it not 1, 2, 3 and 4. We have already solving equation 3 and 4. We get, so if we simultaneously solve this equation, we get a1 equals to minus 4 by 3 and a2 equals to minus 1. A2 equals to minus 1, 4 by 3. So what we get? So we get I of t, I1 of t equals to 7 by 3 minus A1 was minus 4 by 3 e raised to power minus 3 minus e raised to power minus 10 t. So this is the value of I1 of t. Now calculate I2 of t. So remember, you have this equation. So I2 of t is half di by dt plus 4 times I1. So just simply I2 t is equal to half di1 by dt plus 4 times I1. So if we use this equation, so I2t will be equal to so 1 by 2. If I differentiate this above equations, we get uh, plus 4 e raised to power minus 3t minus plus 10 e raised to power minus 10t plus 4 into 7 by 3 minus 4 by 3 e raised to power minus 3t minus e raised to power minus 10t. So overall, the value of I by 2, if I simplify it end to end, the value of I of t, I2 of t will be equal to uh, 7 by 3 minus 10 by 3 e raised to power minus 3t plus e raised to power minus 10t. This is the value of I of t which we get after solving all these equations. So this is the value of I of t. So now we have both I1t and I2t. So now this we have to find out V naught of t. So for V naught of t, remember V naught of t is 1 ohm I1 of t minus I2 of t. That is basically the voltage that is appearing across this. So just minus both I1 and I2 from here, we get V naught of t that is equal to 2 times e raised to power minus 3t minus 2 times e raised to power minus 10t, or we can just simply write 2 times e raised to power minus 3t minus e raised to power minus 10t. This is V naught of t. So this is the answer. So this is how we get the value of V naught of t, or this value of voltage, by solving the second order differential equation, in which by solving a second order circuit in which we only have two inductors as energy storage elements. We do not have any capacitor here, uh, uh, like the ones we solved earlier in example 8.9 and in our previous lectures where we talked about the second order RLC circuits in where RLC are connected in series, and second order RLC circuits where RLC are connected in parallel. So we have so in both of these all of these cases, how we do it, we try to develop a second order differential equation, and we use that differential and we use the initial conditions which given to us or calculated by us, and to solve that differential equation we solve for both transient response and steady state response. And once we have solved for both transient and steady state response, we try to find out the missing coefficients, and once we have these missing coefficients, we find the either value of current and voltage depending on our situation, and using those values we find out whatever the parameters, again current, voltage, power dissipated, power energy consumed, anything in the circuit as per our requirements. So here uh, we are finished with chapter number 8. So we in our next lecture we'll start from the next chapter, chapter number 9, that is related to phasor circuits. So thank you very much for listening.